couple. Yeah, my goal is to finish those today and basically transition over to more routinized lecture format. Last time we've been going through the final two, and specifically we dove into the testing side, sort of risk-driven testing. And I wanted to finish up that discussion before going on and talking about another key component associated with quality assurance, which is peer reviews. Okay. So those are my major goals for today as far as coverage is concerned. Okay, so we had started to talk about the role of risk-driven testing. I made it clear some of the items that were expected of you. And I'm going to expand on some of these a little bit more, particularly in as much as it gets into the DevOps side. Did you folks talk about DevOps in your 370 or 270 or 470 classes? For those who have taken 470, is DevOps and DevOps principles something you've discussed before? Okay. You should be aware of it because it's a pretty much industry-wide set of principles and ideas and organizational commitments that's actually achieved a great deal of prominence within the past decade, certainly, and past 5 years, particularly. And it combines together elements of on the technical side, sort of software development, software engineering, on the one hand, with institutional commitments and IT operations. And I'll talk a little bit about it since you haven't been familiar with it. So we talked about different levels of testing that are expected of you, and I didn't really emphasize it, but it bears noting that, you know, this is called the V model of testing sometimes, and these tests here are sort of paired with corresponding levels of design here, where you know, low-level design is captured by unit test requirements, and the very highest level sort of design documents, as it were, are tested by acceptance tests, and you have these other levels, roughly speaking, being tested by things. The thing I really want you to know here and recognize, I should be sure that I want to be sure that the recording's on. Yeah, is that we have, and I'm going to switch over to my screen here again. Is that we have this this use of sorry, I'm having trouble sharing this, starting this up again. Somehow it's in presentation mode or something. Not sure what's going on. So here we, okay, mumble. Hey, come on, there we go. So we have this different levels of tests, and the different levels of tests test kind of at different levels of abstraction. So unit tests at the most basic level, testing classes of functions. Integration tests, testing how different functions work together or different classes cooperate. You're basically, you may have confidence about each of the pieces, but if the pieces don't play together nicely, if they don't have compatible protocols or expectations, you know, each of them might be right in isolation, might match some specification, but there's some inconsistencies in the specification. Maybe one returns 0 to indicate failure and 1 to indicate success, and the other uses those in a different way, right? It indicates, it takes 0 as indicating success and 1 is failure, or what have you. And so you need integration tests to make sure they play together nicely. And most of our code depends on other code, right? It depends on other code to work properly. And if we just test each piece, sometimes you know, you're not sure how to isolate things to that piece. And this is where mocking comes into play. But so unit tests, we often use mocking to, or stubbing or faking to kind of limit the impacts of other pieces of the system, whereas an integration test, the whole goal is to test things working together. Okay, and you're testing sort of sub areas of the code that are tightly coherent, that use each other closely. System tests, as I emphasized, focus often on user end-to-end tests, et cetera. And acceptance tests here really on making sure the requirements are achieved. Okay. In certain industries, acceptance tests are really very central part of operations. In tightly regulated industries like the pharmaceutical industry, acceptance tests have a whole set of regulations involving them. For example, they might bring in outside testing companies that have an arm's length relationship to verify that the system is working properly, so that they can certify that the system meets requirements of the regulators or something like that. You can have a certification by a third party. And so acceptance tests have a sort of life of their own in some industries and some sub-industries. And I gave some suggestions. This one on the lower right, the use of DevOps practices. And I don't think this was actually in the version of the slide you saw last time. I'll update it. But we're going to talk a little bit about that more today. Okay, so I had some suggestions along these lines. Some of these get into issues with DevOps quite seriously. So the first is you want to plan for a standardized testing environment. What do I mean by that? Anyone? What do I mean by a standardized testing environment? A lot of fancy terms. What do I really mean? What's this whole thing about standardization? Yeah, Lee.
Right? You want kind of a consistent environment where all the versions of things are going to be the exact same. You have all the same software.
Yeah.
And then if you're testing in different areas of your machine, you don't end up having areas just in a different environment.
Totally. This may sound like a minor point, but it actually turns out to be a major headache if you don't pay attention to it. It ends up occupying a lot of your time dealing, chasing problems that are not really defects with the code, but are just due to vagaries of what this person had installed. And it goes into the fact that these days modern software often depends on many, many libraries, many other systems. It's counting on the operating system and libraries of various levels, sometimes, things like DLLs, dynamically loaded libraries on Windows, or corresponding things in Linux, Mac, etc. And if you don't have those standardized, you're going to be getting problems even running it sometimes. And certainly when you run it, you may get spurious issues that the planned deployment environment is not going to have. So you need to standardize your test environment so that the testers and the developers and the production machine all have sort of comparable configurations, exactly the same configuration, so that you're confident if it works on my machine, it'll work on the production machine, it'll work on the tester machine, and vice versa. So this should all be the same. And another need that comes up is resetting the state after the test. Anyone want to say what that means? What do I mean by reset after the test? Yeah.
So if you added something to your database, make sure that you clear it after and clear it out or something.
That's right. Why do we do that? Excellent, Larissa. Yeah, Larissa. Why would you do that? Why is it so important that after the test we sort of clean out what it's changed?
Does it clear the fact that other tests that are going on, or actual system might have, hypothetically, if you had database with people's names, you want to get rid of the names so that it's
good. Yeah, and you're absolutely right. So it affects our ability to reliably run tests and get reproducible results. Like if a test fails once, when we run it once. We don't want to be in a situation just because it altered things like in the database, that if we run it again, it won't fail, or vice versa, right? That it runs fine the first time and then it fails. We want to be able to set it up in a controlled way, sort of like a controlled experiment, like you might run in, you know, biology or chemistry or what have you. You want all the situation to be the same so that testers can reproduce it, or developers can reproduce it. And so, you know, we want to reset the state following the test so we can be confident that if we run that test or other tests, that they're run in a way they won't interfere with each other and it's completely reproducible. So that's a key need. And one of the technologies that's really achieved a lot of currency in this area is what's called containerization. And there's a set of different containerization frameworks, Rocket, Docker, Singularity, or 3. Docker is the dominant one these days. And we talk about Dockerized environments, and containerization is captured through creation of Docker containers. And we create Docker images that describe the configuration we want to use precisely. And what it allows us to do is to essentially say there's a little micro world on our computer. And if you're on a Mac and I'm on a Windows box and someone else is on a Linux box, it doesn't matter. We have a kind of a virtual world inside that's running exactly this version of Ubuntu. It's using exactly these libraries, this setup. It has precisely the same environment, down to the bits that it's accessing. And it's running inside a virtual container that may live on your machine while it's running, but it can't see things outside of what it's told about. So you can enable whether it can use the network or not. You can enable what files it can access. You can enable, you know, what resources it can use. And containerization then allows that code to run in a totally standardized environment. And once that finishes running and you close down that container, other than anything it wrote out that you told it to write out externally, which is through very closely configured interfaces, it disappears and everything is reset. So every time you go back into the container, it starts in exactly the same state, precisely the same state, as if you had a fresh new install on that machine. So containerization is a way of precisely configuring in a machine readable way. You actually have a config file that says what the specification of the test environment is, in a way you can distribute to other people and they can run it on totally different machines and know that they're going to have precisely the same results, the same experiments. So containerization is not alone. This should remind you of another technology that's more general. Does what I described about containerization, this idea of kind of a micro world that, you know, thinks it's the world, but it's running within a bigger environment, does that remind you of any other type of technology? Yeah, Larissa.
I'm guessing you're referring to virtual machines.
Yeah, virtual machines and virtualization. Exactly. So these days, you know, we have boxes, right? That for a computer scientist, that's a box, right? The machines are boxes. We use these terms to mean computers. And you want to be careful using that lingo around people like your stakeholders. You know, we'll get 3 boxes in place and I think you're talking about a pizza box or something, you know. No, so a box here is a computer, but often a given box is going to run multiple virtual machines, which might be spun up for certain needs and spun down for other needs. So we might run on that same physical computer 3 virtual machines that at different times are up or what have you. Or we might have virtual servers, which are each isolated from each other. And the common thing is they're isolated from one another. They're running in what they think is the complete machine, completely configured, but it's specified in software what the configuration is, and you spin them up when you need them, and you can spin them down when you don't want to. And one of the things I did there was to close down my VirtualBox, which is another virtual machine I use to run Windows under my Linux box. So containerization is part of that environment. It's part of sort of the whole philosophy of virtualizing increasingly, separating the vagaries of our physical hardware from needing to have a precisely configured environment that can be used flexibly and even transferred between machines in some cases. Just a couple other things. You want to create a schedule for your testing. When are the testers going to get the code to run? And release criteria is commonly used. So you may have certain criteria for when the incremental deliverable is ready for delivery. You can have no more than one priority one bug or zero priority one bugs and no more than two priority two bugs or what have you. You might want to give that some thought. This class is time boxed, meaning you have to turn it in. So release criteria haven't figured quite as prominently as they do in many areas of industry where they will govern when you turn it in. But you should consider having some release criteria even for release to testers. And then finally, you're going to want to derive some of your testing from your requirements. So at least you have in place a good adoption of that V model. Okay, let's talk about this DevOps issue a little bit more. So DevOps is a philosophy, set of practices and principles and processes associated with that bring together elements of software development with elements of IT operations. Traditionally, in companies, for decades, those have been handled by different groups. The people that did IT to configure the machines that were sitting on the desk of people at Facebook or Microsoft or Google, it's a different set of people that were dealing with setting up the actual products that they were shipping or putting online as services, et cetera. It was a different group of people. The IT folks were kind of in the background just to serve the needs of the company, whereas the folks putting out software as services or as products were a group that the IT folks served. And that had a certain utility to it, but the model tended to break down in certain areas because often the developers have real infrastructural needs that weren't fully being met. And there are certain ways in which the IT staff would be needed to deliver on the developer's goals. And coming out of sort of a rethinking of that relationship was this DevOps, development and operations joined meshing that has caught the software world by storm. And I've listed some of its implications here, some of its emphasis here. You can go read more about it online, and there's tremendous amount of information and talks about it, et cetera. But as far as it impacts you, I'm emphasizing these 7 things. So the use of continuous integration, we talked about that, right? What do I mean by continuous integration? What's one element of it? Is he a hand? Yeah. Name again?
Jeremy.
Jeremy.
Having like a build pipeline.
Yeah, it's a build pipeline's involved. Anytime you push, a build is kicked off. And when people push code, there's a set of build steps that will validate that code, that will run a set of tests. That's the component. The second component, continuous testing. Might run style checkers, might run rebuilds of the database, might run deployment scripts, and beyond that might involve a logging of information, et cetera. So this is this continuous integration supports people in contributing to the repo at any time, not just at the end of day or what have you, and having a whole validation script, set of scripts run that can lead other people to pull their code with confidence. The fact is, once it's contributed, you have high confidence about it. And so other people can get it and start building on it without the fear that they'll break, they'll be getting broken code and then it will break the system. So this continuous testing is a big part of that commitment. It's not, but it's not the only thing. You're testing in the build at a very significant level. You're doing a smoke test for basic validation, and then often you're running some regression tests, some basic tests at a unit test level, an integration level, a system test, just to be sure that it's operating correctly. Another component is release automation. So look, releasing to production, when I'm saying production, I mean, it's not just for testing, it's not just the developers trying it out, it's actually like the live version of this system. That shouldn't be an ad hoc task. That shouldn't be something that's like a one-off thing. Yeah, I'll go and execute this bunch of mysterious commands and get it there. That's fragile. If the right person is out one day, or if they, they're distracted, certain things are on their mind, they might not release it properly. You want to automate that so it's all a smooth process. You can push it out to the servers, the production servers, for example, in an automated way. And that can allow, if you have a problem, re-releasing it quickly, etc. Another component that I emphasize to you is crash monitoring, but more generally, performance monitoring. When I'm talking performance, I don't necessarily mean profiling. Have you ever had a profiling in 370, 270? Like running your code and having under a profiler will mean that you're running your code in an instrumented fashion. What do I mean by instrumented fashion? Anyone?
Checking the how much resources are being consumed and seeing if there's any memory or anything like that.
Exactly, and Shantanu, that's exactly right. So instrumentation basically runs your code, but with other hooks built in so that it's recording some information it normally doesn't record. How much memory it's using, how much time it's taking in different portions of it, for example, and potentially what files it's accessing and all that sort of stuff. And the reason we do that is because we want to know how big a footprint is it having, like on the machine, and are there certain parts of it that are really lagging performance-wise? We have to speed up. Where are the bottlenecks? Bottlenecks in terms of time. There might be 20% of the code that's taking 80% of the time. Or bottlenecks in terms of the memory footprint. These couple areas are taking a huge amount of memory. And we might be able to optimize that. And look, many software developers love tuning code. They love making their code just sing by being really efficient. But the truth is, we don't know what to tune for a big system unless we've done performance instrumentation on it, unless we've done profiling on it. We don't know what to tune because we don't know what the bottlenecks are. We could spend a lot of time tuning parts of it that don't really make a difference. It's 0.5% of the time is spent there, and we make them wicked fast. I mean, what have we gained? But there may be certain parts that are in the, have a lot of use and which are taking a lot of the execution time. And performance monitoring helps you understand the performance of your code, the memory usage of your code, and know if it's no longer available because it crashed. And it'll feed you back information about these. So when it's running out there on testers' boxes, or when it's running even in some users' boxes, you have a sense of, is it crashing? Is it working properly? So if you're publishing commercial apps, and my shop is involved in a number of apps used across the world that have come out of our work. One of the most valuable things you can do is like look monthly, how many crashes did we have on this app that we've gotten out there. How did they occur? What, look at the crash report, you could see what libraries was it trying to use when it crashed. It was trying to do this encryption stuff on an older version of an iPhone. And okay, enough to reproduce it sometimes. So it was an iPhone 6, and it had this version of the encryption library on it or what have you, and it might let you reproduce it. Machine readable configuration setup used to be in this course that the build master would spend a lot of time just manually configuring things from the command line. Set things up and ready to go. And that was okay, as long as things went okay. I remember one year, watch out for this, it's a major risk if you're not careful. One of the teams set up their infrastructure for the class. Things were going great, but they weren't careful enough in one area. One area bit them. They weren't careful enough with the passwords that they were using. And guess what happened? Yes. So there were hackers that broke into their system, and they hacked in, and basically they installed malware on their system. So they had to reinstall the whole thing. And that lost them some critical time in one of the incremental deliverables, because they have to redo the whole manual configuration. You want your config information to be in your repo as a machine readable file so that you can reproduce it, right? So you have it right there in case you need to reconfigure the machine. You don't have to go and type all these commands and go get this, go download that. It should be all reproducible. That's part of DevOps. It's part of the operations side that traditionally someone else was doing for the developers, but should be part of that whole culture of development if you're to really optimize all aspects of it. I talked about virtualization containerization as a key element. That's a big part of DevOps, having in place total ability to reproduce exact environments that clean themselves up and that have precise specifications. And if you go look at Docker, you'll find that it's exactly what it's designed to do. And in fact, you can use Docker images that specify your Docker environment. What environment you want your code to run on, you can use them on Rocket, you can use them on Singularity. So Docker is kind of at the hub of that ecosystem. And finally, and very importantly, attention to the user experience. Like, to what degree are you meeting the needs of your users? Or to what degree are users, shying away from certain areas of your program because it's too confusing? You want to get user feedback on your system on an ongoing basis. So you know about concerns early and you know about them often when they report them. Okay, a couple other suggestions in this prompt before we get into this issue of peer reviews. So something that teams in this class, have issues with. But the truth is, it's one of those things that a lot of teams have issues with. More broadly in software development is skipping tests, the temptation to skip tests on late builds. It says late checkouts. What I mean is, and pushes that occur close to the deadline. So the idea here is, look, we're running up against the deadline. We've got to get that incremental deliverable in by midnight, or we got to ship this code. Whether it's in industry or in the class, the temptation there is, get those bug fixes in to the last minute. And the idea said it's a nicety, you might think, to run tests. We don't have time for running the tests, you might think. What's the problem with that? What's the problem with saying, well, look, we don't have time to run the tests? What could happen? Yeah.
Break more than just that one thing you're fixing.
Say that again?
You could break more than
yeah, exactly. You fix one thing and you've broken another. Or maybe you thought you fixed it, but you just weren't creative enough and trying it, and actually it only fixed a small bit of the problem. This occurs everywhere, and it's especially it's so problematic. There's a term for it, the FFR. Okay. There's a thing called the fault feedback ratio. And basically what it asks is, for all the bug fixes or defect fixes that you think you contributed, what fraction of them actually introduced new problems or didn't fix the problem? You know, the problem still remains, or a new problem is still there. Anyone want to guess what this is? Like for shipping software and development processes. Anyone want to guess? It's between 0 and 1. If it were 1, every time you fix something, you know, it's like 1 step forward, 1 step back. Every time you fix something, you break another thing. That wouldn't get very far. If it's 0, every time you fix something, it's one more thing off your list, and that's it. And you're making progress. Anyone want to guess what this is roughly in commercial software development processes? Yeah. 0.75. So it can be actually most. It's not quite 0.75, but I think it's over 50% for larger changes. So meaning, if you're making changes that are on the order of a couple hundred lines, you're likely to introduce a new problem. If you're making changes that are like a couple of lines, I think it's around 30%. Now, okay, you may say, well, you know, thank you very much for telling me that. What's the implication? To get back to Larissa's point, what's the implication of this for these late checkouts? So if you go forward and you check this in, you push it, and you don't do testing of it, you skip the build parts that are testing it. Chances are it's pretty good that there's another bug in there. And you know, it means it takes a lot longer sometimes to converge to the final product than you think, right? There's a lot of iterations. And later in the game, you know, each of those cycles where you check it in and you go and you test it, and then you got to fix a new problem, that kills you. The time to debug it. If there is a new problem, the time to debug it, the time to fix it, is going to cost more time, and then you got to check it in and test it again. And especially if the testing is not integrated into the build, you're going to be killed by it because you got to wait for the testers to be involved in testing it. You really want this testing going on immediately. Now that's still not going to take away from the fact you still have to fix it, right? Debug it. Okay, so you want to be very careful about this, and it's one of the reasons that, mark my words, it's one of the reasons that products sometimes ship with bugs in them, because they deliberately said, okay, that's the devil we know, right? That's the problem we know about. We can put out a workaround request for it. We can document it. We can live with this. But if we try to go fix it and it pops out, who knows where, it's going to take us a while to go chase those down. It's safer to stick with the one we know. This is good enough. And there's this notion of satisficing that James Bach is famous for, which basically says, look, it's what you're doing is sufficient. You're sacrificing some things, but what you're doing is sufficient for a satisfied customer, and you're reducing the risk that will come from continuing to iterate. You're getting it to them in a time frame that's satisfactory to them. You're sacrificing some things, didn't get everything, but it's enough to make them happy. Okay, you should be planning for some non-functional tests. This gets a little bit to what Shamdun was saying with, you know, stress testing and load testing, performance tests, you know, testing things like with memory footprint, etc. So doing some tests of the load of your code in the system, and it's how much memory it's taking, how long it takes to run. And this is sort of isolation of testing and development environment. You're going to want to use the standardized configuration that's isolated in the sense that it's not tied up with configuration issues that are separate between them, for example. You want testers to be involved in some exploratory testing. Good testing can be put into scripts a lot of the time, but there's a need to try to find new bugs. Exploratory tests are really helpful. Good testers can follow their nose. They say, oh, this area of the system is kind of soft. I noticed some weird things when we tried to do that. It was really slow, or it didn't refresh properly, or it had this problem when I was disconnected, or what have you. It didn't work because of using too much memory. And they go and they try these things. And good testers follow their nose and can often, zero in on some bugs or some real problems associated with it. They push it further. They notice it's taking a while. They give it something more complex, and they keep on pushing it to see if they can get it to really take a huge amount of load or a huge amount of memory, et cetera, and document it. Regression tests, things that for bugs you've already fixed, put them in the automated test suite so that you keep on looking for them, because if they reemerge, you want to know as soon as possible. So something that starts as a manual test, something someone does click, by hand, or that they find through exploratory testing as a problem and report, it should make its way to an automated test that's used, and once it's fixed, it should be used for regression. You should be using test tools. There's this whole universe of testing tools out there. Developers are often not so aware of them. Testing is its own art. It's its own world in terms of the tools, in terms of the techniques, and testers get really good at it. And I want you folks on the testing teams to get good at it. And then I talked about code freezes. Okay, I just want to introduce some terminology here before we go on in our final 20 minutes to issues of peer review. So conceptually, development takes place in stages, and more to the point, issues with the project go through various stages, and defects go through these stages. Some of these stages are not so visible. Some are very visible. And I want to distinguish between them because we have certain terminology we use. So you have to be aware that if you have a defect issue tracking system that lists a certain number of defects for your system, you're going to be very lucky if that's all the defects. Why do I say that? Why do I say you're very lucky? If you have a list of 100 defects, why do I say you're very lucky if that's all the defects?
Because what's to be fixed?
Yeah, the set that you're dealing with in terms of quality problems. Often the bigger issue is what you don't know, right? It's the things you don't know that can sometimes kill you. Those things you know, you can assess them and you say, how bad a shape are we in? How long will it take us to fix these? How serious are they? And you can triage them. You can deal with the ones that are most important and defer the other ones, or warn against them, put out workarounds, what have you. It's the undiagnosed ones that are often the biggest problems. And almost all defects originally start like undiagnosed. That's why I draw them in this first box here. Now, through testing, whether it's formal or informal, whether it's manual or automated, we arrive at bug reports for defects. These are system trouble incidents. We actually don't, the issue is, an issue tracker is a much better term than a bug tracker. We typically don't directly observe the bug. What we observe is a failure that occurs because of some underlying fault that we don't directly observe yet. Testing finds the failure. It says, oh, this thing crashed. that thing never terminated. This thing gave the wrong answer. And those things, get enshrined in bug reports, but that's a misnomer. They should be enshrined in what we might call system trouble incidents, for example, or issues that are found. Now, in this list, which is an explicit list, there may be many duplicates. There may be things that are based on misunderstanding. Someone said this gave the wrong answer, but maybe they were wrong. They actually gave the right answer. They just hadn't realized it. Maybe they misunderstood what it was supposed to do, or were dealing with an old specification. It also may include a lot of duplicates or things that are outdated, etc. And we go through a process called sanitization, where basically we take those reports and we actually wade through them and figure out, okay, which of these are real, unique, current, meaning they're the current version of the system, not outdated, not based on misunderstandings, not so incomplete you can't really see if there's an issue. Maybe someone's reporting something from a version of Android that it wasn't supposed to work on, and you basically ignore those things, and you basically say, okay, what are the real active bugs? So you promote them. Sanitization identifies active bugs. Those are the active defects or the active issues to work on. To say bugs is, again, a misnomer. These are the active ones. And then a process of triage, you figure out, okay, which are really the important ones? Like, which are the ones we want to focus our time on? Maybe there are some that are kind of niceties. Yeah, we'll get around to it. This one is going to be fixed anyway because we're overhauling that part of the system. Let's not put our effort into fixing it until the new version of the system, that component of the system finishes. Or, oh yeah, we know about it. The system doesn't work well when it's disconnected from the web in this way. We know about that. We can live with that. And we'll just warn people or what have you. So triage basically determines a set of important bugs, and then those are, assigned to various developers, either self-assigned or assigned by the dev manager. And then there's going to be, having assigned those to developers and they produce fixes, there's going to be a set that are believed fixed by the developers. So the developer worked on it and they say, I think I fixed that. Notice I emphasize believed here. Why might those not actually be fixed? Why might it be that they're merely believed to be fixed, but not in fact fixed? Anyone? Yeah, Marissa.
The reasons of before, like not thoroughly tested enough, or worse for some cases not.
Yeah. Sometimes the developer is eager to prove their code is right. There's some problem with developer testing. We as developers, we often like to show our code works. So we have sympathetic testing. We test our code to show that it works. And that's a problem because the world is not interested in showing that our code works. And this is one of the reasons testers are a good complement to developers, because their goal is not to show that the code works. Testers often like to show that they can make the code break. And it's a great compliment. But sometimes it leads to some acrimony. Sometimes it leads to some tension between developers and testers. Because the testers want to flaunt, well, I shouldn't say they want to flaunt. They want to say, look, the code broke. And the developers want to say, my code is good. What are you telling me? It's bad code, and there's some acrimony there. So developers often they have a more sympathetic view to the fact that their code works, and they like to believe that things are fixed that aren't really. And so quite a few of these that are believed fixed contribute to this fault feedback ratio, and they end up being identified quickly by the tester. Sorry, that isn't fixed. It still happens. Now, some of these, the reporter, often a tester, sometimes a user, says, okay, it's now fixed. And that goes to what's called resolved. And so it's a result bug, but it's not yet closed. And the test team genuinely, so often the test team sign off is needed to promote it from resolve to closed. And that's like, okay, it's a cast issue. Should still be included in regression tests, typically, et cetera. Make sure it doesn't come up again, but it's basically no longer, something of active interest to the test team. So bear this in mind, that we have these, this kind of stage of a bug's life or a defect's life. And one of the things I want to emphasize, say it now, say it again later, and I'll test you on the final exam, is, testing finds failures. There's a process by which we find the problem underlying the failure, the defect underlying the failure, that's called what? What is going from a failure, an observation of a failure, to understanding its cause found? That's called what? It's a common word. Begins with D. It's debugging. It's a debugging process. That takes a lot of time. And debugging is needed, in order to fix this, right? And you notice that this is a very test-centric sort of picture here that I was identifying, but it bears noting that peer review, the next topic I'm going to talk about right now, directly burrows down to identify faults and not failures. It cuts through all the details to directly looking at code, say, there's a problem here. That's identifying the underlying fault from the start. And it cuts out the need for the debugging side. It cuts out the need for running a lot of tests by allowing it to zero in on the problem. And for that, I'm going to go to peer reviews, which is the major goal here. So reviews, partly in light of what I just said, form a key part of the industry. And there's been huge realization since the 80s when peer review processes first achieved a great deal of prominence within software development. I remember being part of that. That peer reviews have been recognized now as actually more cost-effective than testing. You actually find bugs more efficiently, defects more efficiently than through testing and then debugging. Because you go to the heart of the issue by spotting the faults. And it turns out they find a greater fraction of the defects than does testing. Testing can find a large number of defects, but it's hard to test certain types of things. It's hard to get the system into the state to test it. It's hard to reproduce it or what have you. Whereas it turns out peer reviews actually test a broader set. They really pay for themselves. Like they take time, get together the team for formal inspection, or whatever, it takes time. But it turns out they easily pay for themselves by offloading the team from testing and debugging time and the time to sort of try to fix something, and then it doesn't work, and you iterate on it and all that. And they're more flexible than testing. The amazing thing is you don't even have to wait for the executable code. You can do peer review on requirements documents. You can do peer review on plan for the structure of the deliverable. You can do peer reviews on high-level design documents. You can do peer review on a testing plan. You can do peer review on tests. There's all sorts of things you can do peer review on that don't directly involve executable code. You can do it on a manual testing plan. And therefore, you can get started on it soon. Should be thinking about that. And you can also, in the peer review, address other issues that testing doesn't find, like the clarity of the code, the commenting, the degree to which it adheres to good code practices, stylistic conventions, etc. So early reviews, you should be thinking about this, like UI design for the system. Review it. Do an inspection on it. Requirements documents. Design documents I mentioned, testing plans or another, what sort of tests do we need that would develop confidence this system is working, whether at a unit level or at a level of system tests. You could start thinking about this now. Right now, you could be thinking about the unit tests for your, plate weight study interface or your app. You could start thinking about what might some of the tests be for an app for missing children. Early artifacts have disproportionate impact on development and its success, and you could get going with those sooner. So there's a lot of benefits to lots of people. To the person reviewing the artifact, peer reviews spread knowledge. Why do I say they spread knowledge? Yeah, where is it?
It helps you learn what other people are doing and understand the code they're working on.
Exactly. So if they're sick, at least you know something about how that code works. If they move on to another job, they drop the class. You know basically about how this subsystem works. You can explain it to other people often. And sometimes you learn a coding trick from them, stylistic ideas, and you learn about is that how jest-based testing works in React Native? Or is that how progressive web apps handle this issue of a disconnection from the web or what have you, or persistence of data even when you're disconnected from the web? It also helps the person whose artifact is being reviewed. I mean, it helps them improve their techniques, learn from others, recognize vulnerabilities, right? Maybe their code uses these other pieces of code, and those people who read those are in peer review. And so they could say, well, you should really be doing this when you call my function. You should be, passing at this instead. That isn't how you're supposed to use it, right? And it spreads knowledge throughout an organization, not only about the code base, but about standards, coding styles, etc. And it helps improve the clarity of your code, because people could say, look, it looks like it works, but I don't understand what it's doing. You need to clean it up. You need to refactor it. You need to put it into a couple different, modules or functions or what have you. So there's many parts for peer review. This is from this great book by Carl Wiegers on peer reviews in software that I strongly recommend. There's a couple of books in that area that I think I referred to in the syllabus. Okay, so guidelines for reviewers. It's really important that peer reviews be kept impersonal. The goal of a peer review is not to review a peer. Let me reiterate that. The goal of a peer review is not to review a peer. It's not to say, your coding style is lousy. It's instead to have review by peers of a technical artifact. What I mean by that is, it's asking your peers to help look over this piece of testing code that you wrote, this test plan, this requirements document, this bit of code for this part of the system, and get their thoughts for how you can improve it. How can we do even better? That's the right way to look at it. It's not, why is this lousy? Why is it broken? It's how can we do better with this? How can I improve it? And how can I use these other components of the system better? How can I make it more clear? How can I make it less confusing, etc.? You should keep the peer review team small. I mean, it should be, no more than 7 certainly, and often it's 3 or 4 participants for more informal reviews, and 1 for things like pair programming and peer desk check, etc. And generally, you try to identify but not solve problems in the reviews. They're trying to help, figure out, okay, how could this be improved by identifying this or identifying that without trying to come up with a complete solution. It shouldn't be, a marathon thing, just, no more than 2 hours. And for certain types of formal reviews, you're going to have advanced preparation. That really helps a lot. You're going to want to prioritize your focus on certain things. Okay, so, generally we can put, reviews on a spectrum. And as we'll see, it actually is multidimensional. It's not just one line, but here I've simplified it to one line between most formal reviews and least formal. And you can see there's different types of reviews in each stage. I've asked you to perform inspections, but the truth is I'm not asking you to religiously adhere to all components. So some of your stuff is more like a team review. By contrast, way over here, there's things that are more ad hoc, just checking in on something. Could you take a look at this? That are way down at the other side. And there's some differences in terms used elsewhere. Let's talk about their characteristics. Okay, a review type is shown here on the sort of vertical axis, and then there's the types of activities that take place or not for that review type. And once again, you see the same kind of continuum here on the y-axis that we saw here. We just sort of took this and we turn it on its side, right? So here are inspections. And here are the simplest type of reviews. So ad hoc reviews, you might have a meeting and there might be some correction that you get them to look at, but there's no advanced preparation, there's no planning for it, there's no subsequent verification, but you try to arrive at a correction, let's say. For a peer desk check, you might ask them ahead of time, hey, could you look at this and let's get together and talk about it. You might have a meeting with them or not. They might make comments on that remotely via email. And they might be involved in the fixing process. Pair programming, you're getting together, you're planning, okay, let's pair program it for these 2 hours. There's no preparation involved. There's a continuous meeting. And you're putting in place fixes while you're there, etc. And you go all the way through inspections where you're planning ahead, you have preparation, there is a meeting. Often there's some follow-up outside of the review. There's someone who takes charge of sort of serving as post-review, just double checking things and a verification step. And I'm sort of collapsing correction and verification. Okay, so here, I'm going to distinguish between what's expected of you for an inspection versus more informal things. For an inspection, what I'm looking for in this class, and what's generally advised, is you should have in place someone who presents the code. Now, in a walkthrough, it can be the author. Generally, for an inspection, it's someone other than the author who's presenting. And it helps keep it more impersonal, and it helps the author be less caught up and sort of worry about the presentation and to more look on it analytically or in a more cognitive way. I'm not going to require that. If you want to have the author present, I'm actually okay with that. Okay, and that's fine. But there should be a separate leader who serves as kind of the moderator or the MC, the person who just makes sure that things are coming along with it and the overall plan for the review is being followed, etc. And generally, that's not the author is what I'm looking for. It shouldn't just be the author. For an inspection, generally it's smaller chunks of material, no more than a couple hundred lines. There should be a recorder, someone else who's writing things down. So the author is not getting caught up in it, and the people commenting don't have to go through it. There should be someone else. And often they will end up keeping track of time too. So just making sure time is, we're making progress within the time frame that we need to. And there's particularly participant roles here. I'm here as a reader, and often I'll have like two readers, 2 or 3 readers. So I'll have a couple people commenting on the code, and I'm the author there, and maybe there's the moderator who's leading it, and a recorder who's taking things down. And generally coming out of a review, there's a checklist for things that are found. This is key. You should be in a review coming up with a list of items found. Often you put, where they were found in the system and who reported them, so you can go back and talk about them. Maybe some issues of the type of thing that they were, confusion about this, outdated commenting or whatever, the type of issue that was brought up. So I'd like you to just bear this in mind. I'm not going to ask for like incredibly tight adherence to this, but I would like you to aspire to a sensible combination of how to make use of this approach. And if you want to innovate around it, I'm fine. But please do have, a leader. Please do have someone recording. Please do have more than one commenter, and you should have someone, presenting the material. And there should be ahead of time circulation of material, if at all possible. So, ahead of time preparation, there should be some circulation material. So send out the code to be reviewed, not 30 seconds before the review starts or after review, but well ahead of time. Okay, I think I'm going to stop there. I am providing some slides on best practices for inspections, and good people to include in a review, who include like those who, if you're reviewing code that depends on other things, those people are good to have there. Or if there's other people who use the code being reviewed as by calling it or whatever, those people should be there ideally so that they know how to use it. So think about who's invited. It shouldn't just be any random people. Ideally, it should be the people who are depending on the code or are depended on by the code or the tests or what have you. Okay, that's all. We'll leave it. Remind you, I do have office hours Tuesday, Thursday, and I'm looking forward to seeing anyone in office hours after class if you'd like to come along. Thank you very much.